All right. Hello, everyone. This is the April 12th online hangout for engineering ethics at NJIT. We're in week 12, and we're almost done with this course. So let me go into our lesson here. Yeah, so we're at lesson 12. There are 15 lessons in this course. All the lessons are online already, so we're in lesson 12. The idea going forward here is that lesson 12, 13, and 14 are all about artificial intelligence. Which is our main topic, the final topic we have for the semester. We've done all the hard work. That research project that you have just completed last week and that I'm still grading was the last bit of the hard work for the semester. The last unit of the course is on artificial intelligence. We're going to talk a little bit about what it means for a system to be artificially intelligent, and then some of the ethical implications of that. This is my own personal area of research. I wrote my dissertation on Turing and artificial intelligence. So I like this stuff a lot, and I'm going to enjoy talking about it with you for the next few weeks. So lesson 12 was supposed to be just a warm up to the discussion of artificial intelligence. In lesson 12, we're going to go over some of the philosophical background. We're going to read Turing's famous 1950s paper, Computing Machinery and Intelligence. This is where he proposes the Turing test, which you might have heard of. It's a rather famous test for thinking machines. So I want to go over Turing's views, how the Turing test works and what it means, and then some of the implications. Some of this is a little bit out of date. A few years ago, Eugene Goostman was an AI that supposedly passed the Turing test. I'll talk about what that means. Turing also considers a bunch of objections, and we'll talk about some of these objections. The really big objection, this is sort of my research is partly on this objection, is Lady Lovelace's objection, which Turing talks about some depth. I just flashed a picture of Lovelace. I'll talk to you about Lovelace and what her objection is to artificial intelligence. I'll also probably talk a little bit in this lecture about Searle's Chinese room. This is in the optional readings. You don't have to talk about this. I might also talk about the perceptual crossing experiment a little bit. This is just philosophical background in artificial intelligence, what it means for a machine to think. The idea is that we'll talk this week about the general philosophical topic of artificial intelligence. And then the plan is for the next 2 weeks in lessons 13 and 14 to talk about concrete issues today with regard to artificial intelligence and robotics. Right. So if we're going to talk about sort of future science fiction kind of cases, you can talk about it this week. But the idea is that for the next 2 weeks, we want to talk about real world cases. So in real world contemporary cases that affect us today. So in lesson 13, I want to talk about machine autonomy. Autonomy is the word for self-governance. Auto, self, nomos, governance. Nomos means law, so autonomous systems are self-governing or self-law-giving. I want to talk about self-governing systems, autonomous systems. Someone have a question? All right. I'm going to mute your mic. All right. Thank you. If you have a question, please just ask. But if not, just keep the mic on, or the mute on. All right, so next week we'll talk about autonomy of machines, what it means for a machine to be autonomous, just to sort of whet your appetite. Autonomous machines are machines that can govern themselves, that can act on their own initiative. One place where this touches moral considerations is autonomous weapons. So there's a lot of controversy right now over the use of autonomous weapons, especially in military contexts. This is the SGR-1, built by Samsung. The same Samsung that builds your phone. It's also a military company, builds a lot of high-end military weapons, including this auto turret. Right, so this turret it has cameras on it. It can find and detect motion and then fire on it automatically. When these were first built, they were designed to be automatically firing as soon as they found motion. And South Korea deployed a bunch of these on the demilitarized zone between South and North Korea. Technically, there's still a war going on between South and North Korea. And so they used a bunch of these as, for defensive purposes on the border. But then there was a big humanitarian outcry because these things don't discriminate. Right? They don't just shoot at the enemy. They shoot at anything that moves, which might be innocent civilians. Who knows what might be passing in front of it. So there's concern over having these machines able to decide when they shoot on their own. This is part of the problem of autonomy in machines, autonomous weapons, autonomous drones. Also in military context, there's a bunch of drones, pilotless humanless air vehicles that are dropping bombs all over the planet. But
Hello, can you hear me?
yes, question?
Isn't that kind of much why people fear artificial intelligence? Because you're basically giving a machine that could do harm to humans without a second thought.
Yeah, it's a big moral issue, and there's lots of discussion right now at the UN. In fact, just this last weekend, there was a group talking to petitioning the UN to issue some restrictions on the development of autonomous weapon systems. It's a really big moral controversy. There's a lot of people talking about it, and we're going to spend a lot of time talking about this next week.
But couldn't there be a way, like how the human mind works, like when we're making decisions, we always like think of like either the consequences or the ramifications of that decision. Maybe there could be like a second program that checks and balances the machine's action. Maybe that could work.
Right, and the big question is who's in ultimate control? Is it the machine that's ultimately making the decision, or is there some human that has the final say? Who pushes the button? If someone wants to shoot, does the machine decide when to engage, or does the human? And so part of the controversy over this is who has the final say. And some
Okay.
people think that the humans ought to have the final say, that it should always be a human responsible. And other people think that humans also make mistakes, and maybe our machines can be more reliable. Maybe our machines will make fewer mistakes, in which case maybe the machine should be in charge. I'm going to mute your mic again.
All right.
So one place where this controversy exists outside of the military context is in civilian driverless cars, driverless vehicles, which are increasingly on the road. There's lots of discussion about how humans aren't perfect drivers. They get into accidents. They make mistakes all the time. Maybe these robot vehicles will drive better than us. And again, the question is, do we want these machines in charge of what they're doing on the road? Is it better to have the human in charge of the vehicle, or is it better to have the machine in charge of the vehicle? And again, with humans driving these cars, humans cause lots of accidents. Something like 30,000 people a year, 30,000 people every year die of car accidents. That's a lot of people dead, and if that number could go down with robot cars, maybe that would be better. But that does mean that humans aren't always in control, that sometimes you're giving the control to robots. So there's lots of ethical questions. There's a variation of the trolley experiment that we're going to talk about with drones. There's lots of different things to talk about here. So that's one aspect of the artificial intelligence ethical discussion. And then in lesson 14, we're going to talk about the other aspect, which is technological unemployment. So whether or not we're fighting with these machines, whether or not they're controlling certain aspects of our lives, they're also taking our jobs. Increasingly, jobs are getting automated and being controlled by robots, or being run by robots. So how does this affect the economy? How does this affect the workplace? What is the impact going to be on your careers as automation becomes a more substantial part of the workforce? So these are the two real-world aspects today, talking about artificial intelligence. Again, the plan for this week is to talk about artificial intelligence from a very abstract, theoretical perspective, where we can raise a lot of these philosophical questions. And then the next 2 weeks, we're going to talk about very concrete problems affecting our world today. Lesson 15 is the final lesson of the course, and it's very short. I'll just tell you right now, lesson 15 is just asking you to wrap up. What did you learn in this course? What lessons did you like? What lessons didn't you like? How would you improve this course in the future for future students? Anything else you want to say to wrap up in lesson 15? So, and that's the end of the course. Lesson 15 is the final lesson. There's no quiz for lesson 15. You don't have to do any replies for lesson 15. It's just this final post. So really, the two full lessons that we have, or the three full lessons that we have to do, are lessons 12, 13, and 14. And then lesson 15 is the end. There's no final or anything else at the end of the semester. So we're on the last unit. Does anyone else have questions, comments, or discussion before I jump into the lecture?
I do.
Yeah.
So, on the topic of AI and human pros and cons, from a personal standpoint and from a how would I approach my problem standpoint, I'd much prefer a known decision-making process to an unknown decision-making process. Is that clear? Like, I know an AI is going to do this because it's coded to do that, and it will always do that under these circumstances, versus humans who can have off days, who can be more abstractly manipulated and directly altering the AI's perception of reality or the AI itself. Does that make sense?
Yeah, it makes sense. Although we have to be cautious to not think that the machines will always behave perfectly. Machines also make errors, and the codes that they run are also built by humans, and those things aren't going to be perfect either. So it's a mistake to think that just because it's technological means it's foolproof. In fact, those technologies, and we saw this right at the beginning of the semester, in fact, these technologies build in a lot of the assumptions and a lot of the mistakes that we ourselves make, and so they just repeat them. And,
look in the chat. I posted Google car accident. I'm very familiar with mistakes were made.
mm-hmm.
Yeah, it's just for me. Maybe for some other people, maybe not. There's a certain comfort and assurance in the fact that you know what the operator's thinking. Right? Does that make sense? Because if you're driving a car, you know exactly what the car was thinking. You know why the car did what it did, versus if a person is doing it, because you don't understand the motivations and you don't understand the reasons they do things. Like, for example, on the road, blinkers. I live in PA and nobody uses their blinker, and it's really aggravating, and I don't understand why. It's a safety precaution that nobody uses, versus an AI, which would almost always use the code, because if it didn't, it wouldn't be legal and therefore couldn't be on the road.
Yeah, I mean, I think you're making exactly the assumption that I'm cautioning you against. There's lots of reasons that the car might not put on its blinker. The software could have malfunctioned. There could be a hardware malfunction. The code could be improperly coded. It could make a mistake about what it's doing. I mean, there's lots of reasons that the machine can also make an error. And part of the concern here is expecting the machine to behave perfectly. It gets the machine wrong, and it gets the tasks wrong also. So Turing talks about this explicitly in his discussion of artificial intelligence. Let me go ahead and move on to the AI discussion and start introducing some of these issues. Let me come back to the lesson. All right. Yeah. So okay. So I'm going to be giving the sort of theoretical background on artificial intelligence, and the place I want to start is with Alan Turing. So Turing writes this paper. This paper's Computing Machinery and Intelligence. Here it is. Computing Machinery and Intelligence, 1950. In this paper, Turing is considering the question, can machines think? And in order to appreciate this question, I mean, it's sort of hard for us to appreciate the strength of this question today when we're surrounded by machines that do all sorts of impressive cognitive tasks, or tasks that are mental tasks, thinking, memory, judgment, anticipation. So we're sort of biased here in the present because we have AI all around us about this question, can machines think? When Turing's writing in the 1950s, there were no computers as part of everyday use. Most people had never been exposed to computers except maybe in science fiction stories where there were robots or whatever. So I have this little Prezi. I'm not going to go through the Prezi entirely. I just wanted to point out a couple of things. So prior to Turing coming around, and one of the reasons that Turing is considered the godfather of computing is because he formalizes what it means to be a computer. And prior to Turing, there was no formal definition of computation. We didn't have a specification of what it meant to be a computer. In fact, before Turing, a computer was a job that people had. Here's a New York Times article from 1892. A computer wanted. And the ad is for someone who can do math. Basically, a computer was a calculator in the sense that you did calculations. And you didn't need to know what those calculations meant, right? You did those calculations to keep the books for a business. You didn't need to make the business decisions. You didn't need to understand what the numbers meant. You just needed to be able to do the math to churn out the calculations. So prior to Turing, computer was defined in terms of what human beings could do in this sort of mindless way. You didn't need to be particularly clever to run the formulas. As long as you knew how the formulas worked and you knew how to apply them, then you could calculate anything. So a computer was something that a human being can do without creativity or insight. But hiring people to do computational work is bad because, as we were talking about earlier, humans are slow and you have to feed them, they're expensive. So we've been looking for ways of automating computation ever since. Back in the 1800s, people had actually designed early computers. This is a little piece of the analytical engine by Charles Babbage. He had formally designed it, he had built little pieces of it, but he was never able to actually construct the whole machine. It was 100 years later that we actually took Charles Babbage's designs and using the technologies of the day, built a machine that would work as he hypothesized. And when we built it, it worked exactly as he expected. In other words, it was a computer. It was a turn crate computer. You'd have to turn a bunch of gears, and so all the slots would fall into place. But you would get results. And on Babbage's machine, you can do basic arithmetic. You could even do some simple differential equations. So Charles Babbage's machine was pretty impressive. It was a general purpose computer before any such thing existed, before we even had electricity as a standard thing. So very impressive thing, but no one built it. Babbage wanted money to build this thing, and he never got funding. The politicians didn't see why they should spend a bunch of money on this untested, unproven, very expensive and delicate machine when they could hire someone for a lot cheaper to do the same job. So Babbage's machine never got built. We had to wait another 100 years to build the machine. And I just want to flag this really quickly. When Babbage was designing his original machine, part of, as he was designing the machines, he had correspondence with Ada Lovelace. Ada Lovelace was Lord Byron's daughter, if you know poetry. She was an aristocrat who had an interest in mathematics, and she was a very talented mathematician in her own right. And she ran into Babbage at some parties, and they started exchanging letters, and Babbage described to Lovelace how his machines worked, and Lovelace, in turn, explained to Babbage how he could make certain adjustments and change certain things to compute various properties, various numbers. In so doing, Lovelace is often credited as being the first computer programmer for her work on Babbage's analytical engine. I'm just flagging this because Lovelace is the world's first computer programmer. She sometimes gets recognized as a leader in science and technology, in female science and technology. So there's a Lovelace Day every August, I believe, where they celebrate women in science and technology. And so this is where this comes from. This is Babbage's correspondent, Lovelace. And Turing's going to talk about Lovelace quite a bit in his paper. Right, so Babbage was never able to build his machine, but Turing was able to do it about 100 years later. So Turing, many of you probably know this, you're all engineers. Turing became well known in his early 20s when he proved that the halting problem was undecidable. This is one of the major proofs in the 20th century mathematics. This and Gödel's completeness theorem basically defined 20th century, a big chunk of 20th century mathematics. The point is a little bit difficult to describe, but the simple way of describing is that the question is, can you determine whether a program will halt? For some programs, it's very simple to determine when they stop, when they reach their end state. For some programs, it's very simple, but the question is there any general way of deciding for a general program whether it will stop? And Turing proved that there was no general way for doing this, that the halting problem was undecidable, that you can't know in the general case whether a machine halts. In order to generate this proof, Turing hypothesized what he called the Turing machine. The Turing machine is an abstract formal system. This is a little representation of the Turing machine. It's not a real system. It doesn't actually exist. It's just a little formal tool for thinking about computation in a very general sense. The Turing machine consists of a tape that's like memory with a bunch of cells, and each one of these cells you can write a 1 or a 0 in each of these cells, and the tape extends infinitely in both directions. Right, so you can't actually build something that's infinite in both directions. So it's just a hypothetical tape. And then there's this read-write head. The read-write head can move left and right along the tape, and it can read to and write from each individual cell. And then there's a program that tells the read-write head how to move back and forth across the tape, depending on what it reads from the tape. right? So this is it's a machine. The program determines exactly what this machine does at every step, right? The program and the tape determine entirely every future state of this machine. And so you can look at this Turing machine in order to determine what's going to happen in the future of the machine. And this is how Turing eventually proves that you can't determine whether a general Turing machine will halt. Now, I could go over, there's a lot of technical stuff that we can go over here. The point for our purposes, though, is that Turing gives a formal definition of computation, and with a formal definition of computation, you can actually start building these machines. And so we started building these machines. Once we did, these were some of the first machines to ever perform things like arithmetic, apart from human beings. As far as we knew, prior to the first computers, as far as we knew, we were the only creatures in the universe that could do arithmetic. I mean, maybe there's aliens somewhere else, but as far as we knew here on Earth, the humans were the only creatures capable of this kind of formal processing until we built computers. So within the last 50 years, I mean, it's hard to overstate how important the computational revolution has been in our science, in our technology, in our understanding of ourselves. Prior to these computers, we used to think that we were the only rational creatures. We were the only creatures capable of this kind of formal abstract reasoning. But now we have machines that far exceed us in these capacities. Okay, so and at this early stage, not only were computers completely novel, but we didn't really know how to think about them at all. We didn't even call them computers because the word computer was the name for a job that a human had. So instead of calling them computers, we would call them things like digital or mechanical brains. Mechanical brains fed into some of the science fiction fear and paranoia in the populace, being afraid of these machines. This is, I'm sure you've seen lots of videos of old computers. I'm just going to show you some of the pictures. This is UNIVAC. UNIVAC was the first commercial computer. This whole thing back here, and then all along this wall, is UNIVAC. UNIVAC's first commercial computer. The whole thing is a processor. It's huge, and it's one of the first interactions that the public had with computational devices. UNIVAC in the 1950s, UNIVAC helped compute for the Bureau of the Census. They did the 1950 census, and all that data coming in was processed by UNIVAC. UNIVAC also made a prediction for the presidential race. They predicted that Eisenhower was going to win in 1954. And Eisenhower did win, and so UNIVAC got the prediction right. And all of the newspapers at the time got the prediction wrong. So this is another of the public's first interaction with computers. Prior to UNIVAC and these first big machines, people didn't really have any knowledge of computers, even though they existed. And they existed mostly in war contexts, and so they were secret, and the public didn't really know a whole lot about them. It wasn't until the 50s that people actually started seeing these as big industrial machines, and then not until the 80s, late 70s and 80s, that people actually started working with the machines on a regular basis, that the general public started working with these machines on a general basis. One more just bit of history. After Turing made his name at solving the halting problem, after Turing made his name solving the halting problem, the war broke out, and Turing became enlisted in the war effort. So this is the Enigma machine. The Enigma machine is a cryptographic device. You punch your message into the keypad here, and then the lights highlight here where it's encrypted by some combination of these little wheels and a bunch of plug boards down here. So it would change your message into an encoded version of the message, and then they would send out the encoded version of the message. So using the Enigma machine, the Germans had information superiority in the early part of the war. They were able to communicate with especially their submarines, and the submarines, the U-boats, put a blockade around England, bombed the hell out of London, and England was doing pretty bad. They needed to defeat the Germans, and in order to do that, they needed to crack the Enigma code. But the code was supposedly uncrackable. It was the best cryptographic device that existed at the time. No one knew how to crack it. And even if you did crack it, they changed the codes every day. So takes you 15 hours to crack the code, and then you only have a few hours left before the code's useless, and you have to do it again the next day. So everyone thought this was uncrackable. Everyone thought that the Germans were far superior to us. So England decided to hire Turing because they thought Turing might be able to crack the code, and Turing did. Turing used England's money to build some of the very first computational devices in existence, and he used those as special purpose machines to crack the device. There were a bunch of things that the Germans did in their messages that made it a little bit easier to crack the Enigma code. For instance, Germans always ended their messages with Heil Hitler. So if you knew that that was always going to appear at the end of the message, then that was one of the tricks you could use to unravel the code. Cracking the code eventually helped the British defeat the German blockade and win the war. So let me say that one more time. Turing defeated the Nazis. He's a war hero. And he comes out of World War II as a war hero. He's an intellectual superstar and a war hero. Turing's also gay, which at the time was a crime in England. After the war, he gets arrested because his partner robs his house, breaks into his house, robs his house, steals a bunch of his stuff. And when Turing reports the crime to the police decide to arrest Turing for homosexuality instead of finding the criminal. Now, Turing's war heroes, so they can't throw him in prison. So what they do instead is subject him to chemical castration, which is the punishment at the time for homosexual behavior. Chemical castration means that they're feeding him a bunch of testosterone, right, with the idea that feeding someone testosterone will make them more manly. Of course, this is completely wrong. What happens when you overdose someone on hormones is that they gain a lot of weight and they become incredibly depressed. And Turing eventually killed himself in 1954 by eating a cyanide-laced apple. He was still young. He still had a lot of good work ahead of him. The last things that he was working on were some mathematics of biology, some biological mathematics that's still being used today, that's still being considered innovative today. But the big project that Turing worked on after the war was artificial intelligence, and this question, can machines think? In fact, Turing took it somewhat personally to answer this question. He thinks that the public has a misunderstanding of machines, and that they're afraid of machines in a way that isn't warranted. And so Turing thinks that it's his personal responsibility in some sense to try to change this misperception in the public discussion of machines. And so this is why in the 1950s he writes this philosophy article. He's a mathematician and a logician, but the Computing Machinery and Intelligence article is published in Mind, which is a philosophy journal. And really Turing's trying to talk to the general public. He's not just trying to talk to mathematicians. He's trying to talk to philosophers and really just general people to try to get them to understand what these machines are. Now, Turing doesn't have high hopes for this question, the question, can machines think? In fact, in the article, he actually says that he believes the original question, can machines think, is too meaningless to deserve discussion. He thinks the question is meaningless because it's controversial. Right? What do we mean by thinking? What counts as thinking? Well, there's lots of different answers to that question. People will disagree over how to answer that question. People have been disagreeing about that for thousands of years, right? We have thousands of years of philosophy that go into debating what thinking is, what counts as thinking. And it's unlikely that this question is going to be settled anytime soon. And there's a similar question about machines. What counts as a machine? Is any physical system a machine? Or are machines only certain kinds of systems? Especially at the time when people didn't really understand what digital computers were, calling a computer a machine was ambiguous. It wasn't exactly clear what you meant. So, you can give certain answers to these questions. You can try to defend those answers, but people are going to disagree, and you're probably never going to convince everyone. So Turing thinks that this question, can machines think, is just too meaningless to deserve discussion. You're never going to settle it in any debate. So what Turing suggests instead is to replace the question, can machines think, with a different question. The question he prefers is, can machines pass the imitation game? The imitation game comes to be known as the Turing test. He didn't call it the Turing test himself, he called it the imitation game. In the original version of the imitation game, it's a woman and a man, each trying to convince a judge that they're a woman. So the woman's trying to convince the judge that she's a woman, and the man's also trying to convince the judge that he's a woman. And the idea, this is a parlor game. This is the kind of game that people played before they had TV. And the idea is that the man and the woman would go in a different room, and they would write out their answers to questions. And so the people would ask questions, and then they would get these written out answers in response, and they would use these answers to try to judge who's the man and who's the woman. And the woman is trying to tell the truth, is trying to convince the judge that she's a woman, and the man's trying to lie, trying to convince the judge that he's a woman. And the question is, can you actually tell who's the man and who's the woman on the basis of just this conversation? So in the paper, Turing explains how the imitation game works, and then asks, well, what happens if we replace A in this game with a computer? And the idea is that, can the computer convince a human being that it's also a human? Right, so this is the Turing test. This is a test, right, so where some human is asking questions of both machines and humans. It's getting responses, and it has to use these responses to make a determination, to judge whether the machine is actually human. If the machine can convince the judge that it's human, then the machine passes the test. If, on the other hand, the machine fails to convince the judge that it's human, if the judge can tell that it's a machine, then the machine fails the test. In other words, what Turing is setting as the criteria for intelligence here, right, the answer to the question, can machines think, is settled by indistinguishability from human behavior. If the machine can behave enough like a human, then we should consider it intelligent, just like we consider machines intelligent, other humans intelligent. After all, if a human does something intelligent, it's on the basis of their behavior that we judge them to be intelligent. So if a machine can do the same behavior, if a machine can perform in the same way as a human, then by fairness, we have to judge the machine to be human. In fact, this is Turing's position. Let me write this down just because it's important. So the Turing test is about indistinguishability from human behavior. If you can distinguish between the computer and the human, if the human and the computer don't act the same, then it doesn't pass the test. But if the computer acts enough like a human that another human can't tell them apart, right, that's indistinguishability, and that's passing the test. And Turing's reasoning here, he actually calls it fair play for machines. He says it wouldn't be fair to judge the machine by any standard other than the same standards we use to judge human beings, right? So in this class, I judge your work on, I have a rubric for judging your work, for judging the quality of your work, and that's how I grade all the students. And to be fair, I grade all the students the same. So if there was a computer taking my class and it was trying to write essays for the discussion forum, it would only be fair to judge that computer by the same rubric that I'm judging everyone else. It wouldn't be fair to judge the computer by a different rubric that judged them more harshly. The only fair way is to use the same rubric for all participants, right, for everyone who's taking the class, whether they're a machine or a human. Right? This is fair play for machines. When Turing says fair play for machines, he doesn't mean that we should treat all machines like humans. He doesn't mean that all machines deserve equal treatment or respect or anything like that. What he's saying is just that we ought to use the same criteria for judging all the things. Right? So in a human being, if they do well at their exams, then I judge them to be intelligent. And if a machine can do well at those same exams, then I have to judge the machine to be intelligent as well. Now, in the Turing test, the indistinguishability isn't in general. The indistinguishability is specifically in conversational language use. In other words, if you engage the machine in a conversation, can it talk to you like another human being? Can it hold a conversation with you like another human being? Right, so this isn't all kinds of intelligence, right? This doesn't guarantee that the machine can do math well, or can, write a poem, or paint a painting, right? There's lots of things that human beings can do that isn't guaranteed by a machine that can pass the Turing test. All of the Turing test requires is that the machine can engage in conversational language use. There's a question?
Yes. I just, in the chat, I just posted like a video of this new companion robot that's being invented in Japan called Pepper. Um, it's like but this robot, it can mimic emotion and it can recognize emotion, but like does that generally mean if that it has emotion?
Excellent question. Yeah, Pepper's awesome. I have a link to Pepper on the lecture. I have a bunch. Actually, I have a bunch of these videos. Let me go ahead and show some of this. Yeah, so this is Pepper. I have a link to a bunch of different robot videos on the lecture. Pepper and Hector, Mayan. So this is Pepper. Pepper behaves in ways that are emotive. In other words, it's not just giving logical outputs, but it's giving outputs that are supposed to be expressive of emotion in order to get people to interact with it better. Right? The idea is that you'll be more likely to interact with something that's social as opposed to just purely robotic. Now the question you asked is, does that really count as emotions? Is Pepper really being emotional, or is this just acting like emotions? Right. Yes. That's the question. Yeah.
Yes.
So Turing's position here is that at bottom there's really no difference. If you can act sufficiently like a human being, if you can express emotions that look enough like a human being, the way the human being expresses emotions, then we should also consider you as having emotions. And here's Turing's argument. Turing says, look, I can't see inside of your head. I don't know what's going on inside of your mind. But I still think that you have emotions, right? I can't see everything that's going on in your head, but I still think that you have emotional reactions, that you have feelings. And the reason I think that you have emotions and feelings is because I see your behavior. I see sometimes you get upset and you're angry and you stomp around and you huff and puff, and then other times you feel sad and I can see you crying, or other times you're happy and I see you laughing. Right? I see your emotions in your behavior. I don't see your emotions themselves. I see the behavioral consequences. So it's from your behaviors that I judge you to be emotional. And then by the criteria of fairness, Turing thinks that if we want to judge a machine, we should also judge the machine by how they behave. So if the machine is behaving in enough ways to seem like they're emotional, then that's enough to be emotional. So does Pepper act sufficiently like a human to judge it to have emotions? Well, maybe not. Maybe Pepper's not there yet. Maybe it's convincing to some people. Here's a better example. The other day, some of you might have seen this. The other day, Microsoft released a Twitter bot called Tay. You might have seen this. Tay learned to interact with people on Twitter, and within about a day, Tay turned into a big racist, tweeting about Hitler and the Jews and hating feminists and this kind of stuff. All of this stuff was learned immediately from interacting online.
But if you think about that, that's probably the user's fault for giving that system all that information.
How do you mean?
Like most of the time when you're in the internet, well, I would say most. Like some people think half or like briefly. You always hear like racist, sexist, like all these different hate comments in the internet that were just generated to like either troll somebody, quote unquote troll somebody, or just be a hateful person in general. So it might have been like what Tay learned from us or well not from like all of us, but from other users and like other accounts of how they interact with each other.
Right, you're absolutely right. I mean, Twitter's there's lots of racism on Twitter. There's lots of other good things on Twitter, but there's lots of racism on Twitter. And Tay's just picking up on that and then reflecting it back. But the thing is that this is what human beings do also, right? A human being that is racist isn't racist like because of something deep inside of them. They're racist because they learn to be racist by growing up in a racist community, right, with racism all around them. So when Tay does the exact same thing, right, Tay learns to parrot her social surroundings. Tay's doing the exact same thing. You expect. So we should judge. I mean, if we judge a human being to be racist because they parrot their surroundings as they grow up, when Tay does the exact same thing, we should judge her to be racist too. Look, she's saying a bunch of racist stuff, and she learned it from all the people that she's interacting with. That's exactly what racism is in human beings. So why not judge Faye to be racist also? The general point here. So I'm gonna mute your mic. Sorry. Good question. The general point here is that we want to judge the machines on the same criteria that we judge the human beings. Turing thinks that we shouldn't judge the machines based on what they're made of, based on what's going on inside of them, because we don't always know what's going on in humans, but we judge human beings to be intelligent. And if we judge machines any differently, this is unfair. Turing thinks it's a bias against machines. Turing's worried here that we're biased, we're unreasonably biased against the machines, that just because it's a machine, we immediately conclude that it can't be intelligent. And Turing says that's not fair. What we should be looking at is what the machines can actually do. If their behavior is the same kind of behavior that we judge to be intelligent in a human being, then we should also judge the machine to be intelligent. So one way of understanding the Turing test is that it's a way of getting rid of these biases, right? The judge doesn't know if the machine is a machine or not, right? So it can't bring in these prejudices beforehand, but it has to actually interact with the thing and then see what happens as a result of that interaction. If that interaction is the kind of thing that you would expect from another human being, then you judge it to be intelligent. And if it happens to be a machine, well, then you just shown that a machine is intelligent, right? Because look, it's doing intelligent things. The best example of this is Kasparov versus Deep Blue. Was there a question?
Yes.
Yeah.
Not a question, though, in so much as an observation about the nature of intelligence and what we're dealing with. So, if we operate on the assumption that machines have the capability to think and to be intelligent, and I'm wording like that to avoid controversy, then are we not presented with the ultimate opportunity to learn the definitive answers to nature versus nurture? What would happen if you took a machine designed for military purposes and gave it the equivalent AI of a nurse droid? What would happen if you did the same thing backwards, vice versa? So, I mean, we're dealing, at least to me, we're dealing with more than just machines. We're dealing with a fundamental question of intelligence and what it means to think. Does that make sense? I'm not crazy?
Yeah, we're dealing. So Turing thinks that you can't answer the question, can machines think? Right? You have to answer different kinds of questions. And the question that Turing's interested in is, can machines behave enough like human beings that it fools us into thinking that they're human? Right? So indistinguishability as a criteria for intelligence.
I have a question.
Yeah.
Okay, then this is my thing. You're saying that we can't convince, right? Like we can't. If they can act enough like us, then we can't distinguish. But then again, can you say the same thing like about a psychopath? You know, psychopaths don't really have emotions or whatever, but they do imitate. You know what I'm saying? So they do make you believe that they do feel emotions, that they do feel love or hate or whatever, but they don't. So isn't what I'm saying is how can you simply say, you know, if the whole entire emotion, then how can you say if a robot makes their emotions seem so much like a human, then maybe they are expressing emotions. So psychopaths do the same things, but they're not expressing emotions. They're just lying. Do you get me?
Yeah, so you're worried about deception. You're worried about people who are making it seem, and of course this is the case. I can make it seem like I'm, sad and crying when in fact I don't care at all.
Mm-hmm.
This is possible. By the way, let me go ahead and say right now that the word of the day is fair play. Fair play is the word of the day. If you put fair play on the sign-in sheet, you'll get credit for today's.
What's the word of the day?
Fair play.
Fair play. Okay.
Fair play. Fair play. Fair play. So the question. So the question that was asked was about deception. Was about sometimes people deceive us. Sometimes people act in ways that don't actually reveal their real inner emotions, or maybe they don't have any inner emotions. There was a couple of parts of this question. One part of this question was, can't we build a machine that behaves like a psychopath? In which case, you don't have to build it to have internal emotions, because those people don't. I should say, just before I go on, that psychopath isn't an actual psychological designation. There's no psychopath in the DSM. There's other kinds of personality disorders that people might have, but psychopath isn't among them. But yes, so you can behave like a person. I mean, technically, someone who's in a vegetative state is technically a human being, and it probably wouldn't be very hard to build a machine that behaves like them. So maybe building a machine that behaves like humans is too general of a phenomenon. Maybe we want something more specific. This is why Turing isn't saying behavioral indistinguishability in the general case, but he starts talking about conversational language use. If you can hold a conversation with the machine, then that's... And the idea is that, if you can talk to someone, I mean, this is usually the basis that we judge anyone to be intelligent. If I judge you to be intelligent, it's usually because I've talked to you for a little bit, and I can tell from the words that you say, from the things that you say, that you're an intelligent person. Sometimes if I talk to you long enough, I can also find out that you have no emotional responses, right? That you're a heartless monster. I can also figure that out by talking to you. So I can figure out a lot about your internal beliefs and desires from just this conversation. And the idea is that we want to hold the machine to the same standard. We want to see what the machine can do. And if the machine is behaving in a way that we would expect of someone who has complicated internal states, then we ought to judge the machine to have the same kinds of states. Okay, go ahead.
What with machines, there's always like a fear of them being self-aware. What will be like let's say I'm just gonna give an example. Let's say a nursing robot that was built for nursing, like, want to go against its programs and prevent humans from getting injured rather than treating the injuries. Wouldn't that be a possibility? Like, mainly like machines going against their programming. Couldn't that be like a bad thing, like how we see it in movies, or could it be a good thing, kind of much how I described before? What are the possibilities of it?
Yeah, so I think machines are already self-aware. I think the phone in your pocket is self-aware to a certain extent, and I think it also violates programming. I mean, it's buggy. Sometimes my phone crashes, and I don't know why. Right? Is that violating its programming? Well, I don't think machines do everything that we tell them to do, but people don't always do what we tell them to do. Our whole social systems are built on the premise that not everyone's going to be a cooperator. Sometimes people are going to be defectors. Sometimes people are not going to have the general interest in mind. And that's true of humans as much as it's going to be true of machines. I don't think machines make a unique problem here. Everyone can possibly not play fair. And I think, in fact, most of the time we have more to fear from the humans for not playing fair. But let me go on, because I want to get to some of these points that I haven't gotten to. I especially want to talk about the Lovelace objection. So, and I need to let me go back. If you come to lecture tonight or on Friday, I will have lecture on Friday. I'll talk about this stuff more. So, yeah, question?
Yeah, just before you continue, how do you personally define self-aware? Do you mean it can reference itself for answers or solutions? Or do you mean it can come up with inventive problems or solutions to problems?
So yeah, no, it has nothing to do with solutions to problems. Self-aware just means that it has a model of its own behavior, that it uses a model of its own behavior to adjust its behavior. So your cell phone, for instance, takes account. Most people's cell phones take account of like battery usage, and it'll dim the screen if the battery's low. This is a kind of self-aware behavior. It recognizes something about its own state, namely that its battery is low, and it adjusts its behavior on the basis of its own recognition. I will show you more elaborate forms of robot self-awareness if I get time.
That just seems a lot less loaded of a question than I thought it would be.
Yeah.
Because the idea of self-awareness in robotics is more, it's self-aware, like dun dun dun.
Yeah. I think you're right. I mean, this is the science fiction bias that we have. So there's two things going on here. One is we tend to think that human beings have some special mental properties that makes them radically different from all the other creatures. This is false. Human cognition is not particularly special compared to the other creatures. And from this perspective, it's not very hard to replicate lots of different aspects of human intelligence. In fact, we can do better in machines, at least for some aspects of human intelligence. And it's increasingly, there's increasingly few things that we can do that only human beings can do. Let me put something up here. Sorry about that. Yeah, this is one of my favorite pictures. Here's a human standing in a box with on the wall these pasted words. Only humans can hold press conferences, only humans can clean the house, only humans can drive cars, only humans can translate speech. Here's the human race frantically writing down these things that only human beings can do. And then here on the floor is the wreckage of things that used to be on the walls but are no longer. Only a human can improvise jazz, only a human can understand continuous speech, only humans can process natural language, only humans can recognize faces. Nowadays, human beings can do not. So it used to be the case that human face recognition was the best on the planet. We didn't know anything else that could recognize faces as well as us. Now computers beat humans at face recognition. This happened in 2014, that we started building algorithms that can outperform humans in detecting faces, that a computer is better than a human at recognizing the same person across multiple pictures. It's only within the last few years that computers have passed us in these respects. And there's still some things that maybe only human beings can do. Only a human being can play soccer. But these things are getting ticked off the list very quickly. And on Turing's view, there's not a general question of whether the machine is intelligent or not. The question is, can it do this task well enough to compete, to match forces with the human? Right? Conversational language use is a great example because it requires two participants, right, interacting together in the right sort of way. A better example of this are things like games. So chess. This is Gary Kasparov. Back here is the computer interface for Deep Blue. Deep Blue is an IBM machine. If you want to know when computers took over the world, it was in May of 1997. May 11th, 1997? Yeah, May 11th, 1997. When Kasparov played Deep Blue chess. Deep Blue is the IBM computer, supercomputer. It can calculate 1 billion moves a second. Kasparov is the best chess player of all time. At the time, he was the strongest chess player that we thought had ever lived. Kasparov, so they rank chess players. You start off as a novice and you become a master, and then the grandmaster is the highest chess rank. And they used to say that there were the grandmasters, and then there was Kasparov in a league of his own. Kasparov could play multiple. He would do these exhibition matches where he would play 3 grandmasters at the same time, all 3 grandmasters across the table from him, and him playing a move on each board and then moving down the board and playing the others. And he would beat all 3 grandmasters at the same time. Back in the early 90s, he played the entire world of chess. It was the early internet. You could log onto a website and vote for what you thought the next move should be, and then it tallied all the votes, and whatever the majority vote would win. It was Kasparov versus the world, and Kasparov kicked the world's ass. In a democratic situation like that, people tend to vote safe. They tend to vote for the safe move, and Kasparov, an expert at Kasparov's level, could easily deal with the safe move, and so Kasparov destroyed everyone on the planet. Kasparov had also played a bunch of computing chess computers. Even Turing, back in the 50s, had started toying around with some chess playing software. It wasn't very good. But Kasparov had played against some of these computers before, and he'd beaten a bunch of them before. None of them had really stood their ground against Kasparov. Back in 1996, Kasparov played an exhibition match against an earlier version of Deep Blue that wasn't as good. Deep Blue won 2 matches, but Kasparov took 4 in the tournament. After that tournament, Kasparov's like, look, we're not anywhere close to a computer that can beat a human being at a sustained chess. I mean, they're clever, they can play some good games, but the kind of skill required to defeat a grandmaster tournament level is just not there yet. So the next year, IBM comes back and challenges Kasparov to the game again. In this game, Kasparov wins the first game, and after this first game, they have a press conference where Kasparov again says that he doesn't think that it's time yet. It might be another decade before we have chess-playing computers that are good enough to compete with humans at the grandmaster level. And then game 2 happens. Game 2, it's only the second game of this 7-game set, or 6-game set, but game 2 is the game where Deep Blue won. In this game, Deep Blue ends up playing a move that sacrifices its queen, but for better board position. The queen's the most valuable piece in the chess game, and it's a very risky move. And Kasparov just wasn't expecting it and couldn't deal with it. After that move, Kasparov was shaken, and he never recovered. For the rest of the game, he gets ties for the rest of the game. Deep Blue wins the last game, and he ends up winning the match. In fact, Kasparov was convinced that no computer could make that move, that there was someone behind the scenes cheating for IBM with the Mechanical Turk. Chess is the game of kings, and kings used to like playing chess, but kings didn't like to lose at chess. And if you were to beat a king at chess, then you could lose your head, depending on what mood they were in. So people used to throw games to kings, and then kings would go around thinking that they were a lot better in chess than they actually were. And so someone who was not happy that Napoleon thought he was a good chess player built this thing. He called it the Mechanical Turk. He said it was a chess-playing computer, chess-playing machine. This machine would play chess. In fact, it wasn't really a machine. It was just a human being hiding inside this box, and the human being was playing the chess instead. But the machine beat Napoleon because the machine was the only one that was brave enough to beat Napoleon. And this is what Kasparov accused IBM of doing. Kasparov accused IBM of hiding a grandmaster in the background that played this very risky move in game 2. Kasparov demanded to see the logs from Deep Blue. IBM never released the logs after this match. And in fact, right now, Deep Blue's sitting in a basement somewhere. IBM's not letting people see it. But it doesn't matter, even if Kasparov's right about the cheating, because nowadays you can buy off-the-shelf software at Best Buy and play it on your laptop at home. And that software can beat even the best grandmaster. It can wipe the floor with Kasparov. There's no competition anymore between humans and machines. Machines are just much, much better than humans. And I think I mentioned I might have mentioned this some other time. I think I mentioned this in the live lecture. But just the other day, Google challenged Lee Sedol, who's a 9-dan at Go. So even after Deep Blue won at chess, people were like, well, chess, okay, maybe a computer can beat a chess, but no computer's going to win at Go, because Go is infinitely more difficult. In chess, you have an average of something like 35 moves that you can make per move that you have to consider. And in Go, you have something like 300 different moves that you can consider at any one time. It's just a much bigger problem space. And just a few weeks ago, beginning of March, Google's computer AlphaGo beat Lee Sedol at this game. I haven't won one more of these games in the lecture. I have this discussion on IBM's Watson, who played Jeopardy against our top-ranking Jeopardy players, and Watson beat our best Jeopardy players at Jeopardy. Jeopardy is a different kind of game than both chess and Go. Both chess and Go, you can imagine, are kind of formal games that you can assign equations to. But Jeopardy is a little bit harder than that. Jeopardy requires, where is my, oh, there's. Jeopardy requires understanding the words, understanding sometimes wordplay, sometimes obscure references, right? You have to have a vast background of knowledge, but you also have to have some linguistic processing skills to understand the questions and to give the right answers. None of that's trivial, and the fact that we can build these machines that perform better than our humans is quite impressive. Remember, on Turing's criteria, it doesn't matter what you're made of, it matters what you can do, right? And we should judge the performances of the machines by the same standards that we judge human performances. So Kasparov plays really good chess. It's because Kasparov plays really good chess that everyone thinks that he's intelligent. Some people call him a genius. It's because Kasparov plays good chess that people think he's intelligent. When Deep Blue plays Kasparov chess, Deep Blue can beat Kasparov at chess. So if we're playing fairly, then by the same standard, we should judge Deep Blue to be intelligent. Right? The very thing that we judge Kasparov to be intelligent, Deep Blue performs better. So by fairness, we should judge Deep Blue to be more intelligent, to be intelligent as well. Right? Ken Jennings is good at Jeopardy. Watson can beat Ken Jennings at Jeopardy. Therefore, we judge Ken Jennings to be intelligent because he does well at Jeopardy. So we should judge Watson to be intelligent because it does well at Jeopardy too. So there's lots of other stuff to talk about. I'm sort of running out of time, so I'm going to run through this. In Turing's paper, he gives the imitation game as an alternative to the question, can machines think? He doesn't think we should ask what the machines are made of. He doesn't think we should ask how they're processing. We should ask what they do, what tasks are they capable of performing, and what is how good is their performance? Does their performance match human performance or exceed human performance? And then once he gives this imitation game, he starts considering objections. He considers a bunch of objections. Some of them are better than others. One objection worth noting here is the argument from consciousness. This is in the paper. Right, actually, let me just pull up the paper. Argument from consciousness. This is Professor Jefferson's oration. He says, not until a machine can write a sonnet or compose a concerto because of thoughts and emotions felt, and not by the chance fall of symbols, can we agree that machine equals brain. He says, no mechanism can feel pleasure at its successes, grief when its valves fuse, be warmed by flattery, be made miserable by its mistakes, be charmed by sex, be angry or depressed when it cannot get what it wants. Turing considers more elaborate things of this on the next objection, the argument for various disabilities. Right? The idea is that there's some X that machines can never do. Machines can never be kind, be resourceful, be beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries and cream, make someone fall in love with it, learn from experience, use words properly, be the subject of its own thoughts, have as much diversity of behavior as man, or do something really new. These are all things that they claim machines can never really do. Turing's response to these arguments is not to just assert that, yes, machines can do them. Instead, his argument is to say, well, how do we know that humans can do these things? Right? How do we know that humans are intelligent? How do we know that humans are conscious or have feelings? Turing says the way that we know humans do this is by looking at their behavior. So if a machine can illustrate the same behavior, can demonstrate the same behavior, then we should judge the machine to be intelligent also. Right? So here's a passage, a little passage between a human and computer interrogator. And the idea is that if the computer is giving responses like these, right, where these responses understand that a Christmas day is different than a winter's day, and that a Christmas day is a flattering comparison, but a winter's day is not a flattering comparison, and that picnic wants to be flattered. Right? These are all things that the computer has to understand in order to be able to engage in this kind of conversation. Right? It demonstrates a certain level of intelligence and understanding to be able to have this kind of conversation. Sensitivity to poetry and nuances of language and all that. So if the machine can demonstrate this kind of conversation, we should judge it to be intelligent in the same way that we judge a human that gave the same kind of response. Yeah. Right? I don't know how your brain works. I don't know how the brain creates all the sophisticated thoughts and feelings that you have. But I still judge you to be intelligent, and I judge you to be intelligent by your behavior. So when a machine can perform in the same way, can exhibit the same behavior, then we should also judge the machine to be intelligent. Okay, so let me do a 5-minute presentation of the Chinese room. Actually, well, let me do 5 minutes on the Chinese room, and then let me do the Lovelace objection very quickly, and then we'll go on. So, Chinese room. Actually, I'm not going to do that. I'm going to skip the Chinese room. I'll talk about the Chinese room in live lecture tonight, and maybe on Friday, if you want to talk about it. But I want to go into the Lovelace objection because I think the Lovelace objection is more common. Chinese room is a little bit of an esoteric objection. The Lovelace objection is very straightforward. Ada Lovelace, in her letters to Babbage, says that the analytical engine, Babbage's machine, has no pretensions to originate anything. It can do whatever we know how to order it to perform. In other words, the machine only does what we tell it to do. It doesn't do anything original on its own. It only does what we've told it to do. Now, notice that Lovelace says that it can do whatever we know how to order it to perform. So Lovelace doesn't deny that machines can do intelligent acts, perform intelligent behaviors. Right? There's nothing that's off limits from the machine as far as what the machine can do, as long as we're clever enough to program it to do those things. Then the machine can do anything. So Lovelace is not denying the possibility of machine intelligence. Lovelace agrees that machines can behave intelligently. What she denies is the possibility of machine autonomy. She denies that the machine deserves credit for what it does, because it's not really the machine doing it, it's us doing it. Right? So Deep Blue didn't really beat Kasparov at chess. Deep Blue doesn't understand chess at all. Deep Blue is able to do well at chess because we've programmed it to do well at chess. So really, we've beat Kasparov at chess with our sophisticated tool, Deep Blue. Right? Deep Blue is just a tool, and we're the people that are wielding the tool. We've got the hammer. Right? So we're the tool users, and the machine is just a tool. So we're the one that gets credit for all the intelligence. And the machine doesn't get any credit at all because it's not the one that's in charge. It's not the autonomous one. I think this is the most common objection to artificial intelligence, that it's not the machine that's really the source of these behaviors. It's really humans who are the source, and so we get all the credit. So Turing addresses this objection explicitly, and he's got two responses. His first response is that machines don't always do what we tell them to do. Sometimes machines surprise us. Right? Sometimes machines take us by surprise. They do things that we don't expect. Anyone who's ever worked with a computer knows that the machines don't always do what you tell them to do. Sometimes machines do all sorts of weird things that who knows why they're doing that. Sometimes my machine crashes and it breaks down and I can't fix it, and then I call on technical support, and the technical support operative also has no idea what's going on, right, and suggests that I just reinstall Windows or whatever. Right? In these cases, everyone who should know what's going on in the machine has no idea what's going on in the machine. The machine's behavior is not explained by anyone's intentions for using it. That doesn't mean that the machine is intelligent on its own. It just means that the machine's not under our complete control. Right? We can't always anticipate what the machine's going to do, because just like us, these machines are also fallible physical systems. There could be an electromagnetic spike that causes the bits to flip randomly. Who knows? Right? Lots of things could happen. These are all physical systems, and they're all going to be imperfect. So the machines aren't always under our complete control. And this is kind of the presumption of Lovelace's objections. Lovelace's objection is that machines always do what we tell them to do, so that we have total control. And this, someone was saying earlier about that I think Bailey was saying that it's better for us to have knowledge of what the machine does, right? We know everything that's going into that machine, whereas people are random and who knows what's going on with people. Well, I mean, it's not true that we know exactly what's going on in these machines. Sometimes we don't, and sometimes we can't tell what's going on in the machines. This is especially true as these machines get more and more complex. This isn't enough to prove that they're intelligent, of course. It's just enough to show that we don't have control. So Turing needs another argument, and he gives a second response later on in the paper under the rubric of learning machines. Turing says, if you want to build an intelligent machine, don't try to build a full human brain. Instead, try to build a child's mind and allow it to learn from its environment. If a machine can learn from its environment, then the results of its behavior are not its alone, but they're the result of its let me say that again. If a machine can learn from its environment, then its behavior is not the result of only what we told it to do, but they're generally the result of what the robot did in the world, what the machine did in the world. Right? It's learned from its interactions with the world, so its knowledge is a product of its existence, and it's not merely a product of our programming. Right? So this is machine learning, and this is really Turing's major contribution. Nowadays, the word artificial intelligence sometimes has negative connotations, especially in the public. People have all sorts of objections to it. So nowadays, most people who work on artificial intelligence call it machine learning, and the idea is that you learn from data sets, you learn from your environment. So I've got a bunch of examples of this on the website. My favorite here from Cynthia Brazil. Cynthia Brazil is my favorite roboticist. She works at MIT, the Media Lab. And she has a long career of building social robots. Kismet is her first robot back in the late 90s. Kismet's supposed to be an emotional robot where it's expressive, where its face moves in ways that you would expect from humans emoting. And Cynthia Brazil has built other Cynthia Brazil has built other robots to continue this learning trend. The most sophisticated of these robots is probably Leo, and I have 2 of these videos here of Leo learning. And you can see a demonstration of Leo actually learning from its environment, that the things that it does are not a product of how it's programmed, but are a product of what it's learned, how it's interacted with the world. These are all at very rudimentary stages, using developmental psychology, using the psychology of children. So these robots have the intelligence of like 3-year-olds or 5-year-olds, but that's the idea here. Then I have a bunch of other robots. Some of these, like we saw, Pepper is emotional. Hector is really awesome. Hector is a self-aware robot, and it's self-aware in a very sophisticated way. It's aware of its own body structure, and so it learns how to move its body. It learns how to walk by moving around and seeing what it can do. So it starts off with no preconceived notions of how its body is structured, and it learns to use its body through its interactions with its environment. There's lots of other these kinds of things. This isn't a robot. This is just a AI program. But it teaches itself to play video games. This is a machine that will play a game and lose and learn from its mistakes to improve its performance over time so that it maximizes its score. This AI will quickly, over a few thousand games, learn to master any of these games. So it can learn to master Mario Brothers or Breakout or whatever. In fact, these machines can quickly start to perform much better than a human being. This one I like. I guess I'll just end here. I have a lot more to say about robots, and I'll be talking more about robots over the next few days or few weeks. Let me pull this up over here. So C. elegans is a nematode. It's a animal model. In biology, they have a few animal models that they study as like a general animal. They learn about general animals from studying this one animal very closely. So like the mouse model, scientists often study on lab mice. The mouse model is supposed to be the model for all mammalian behavior. Well, it's supposed to be the model for all general animal behavior. This is the nematode, C. elegans. C. elegans, widely studied. We know a lot about C. elegans, including its entire genome. We've sequenced its entire genome, so we know every gene in C. elegans. But more importantly, we've sequenced its entire connectome. The connectome is the wiring circuit for the brain, for the neural architecture, right? Where are all the neurons and how they all hook into each other, and how those neurons hook into the muscles and the rest of the organism. So for a human being with trillions of neurons, this is very difficult to do. But for C. elegans only has like 350 neurons. And we know exactly where all those neurons are in its body, and we know how it hooks up to the rest of the machine. So, because we know every neuron, we can build a simulation of that system and put that simulation into a robot. So this is a C. elegans robot, if it loads. Yeah, so this is the software, and this is just a software encoding of the exact connectome of C. elegans, where all the neurons are hooked to each other the way they normally are, and all the outputs of that system are hooked into the actuators of this little robot. So this little robot is controlled by C. elegans' brain. This is a robot that's moving around the world on the basis of a simulation of the neural architecture of an organism. Right, this is an artificial organism. This is exactly what C. elegans would do if it were getting the same kind of neural inputs as this robot's getting. Right, you can see this when you see C. elegans moving around, it sort of goes back and forth. If it bumps into something, it'll back up, and that's exactly what you see this robot doing. Right, so this is an artificial organism. So I've just started this discussion. Obviously, there's a lot more questions that people have. Our conversation today was great, everyone, and I hope you guys can continue this conversation on the website in the discussion forums. I'll try to engage you there also. I'm out of time. Thanks, everyone, for showing up. I'll talk to you next week. Bye.